So hopefully what we got here is a little bit of a short one, just a refresher. So we talked back in Unit 2 about alpha halogenation, and we mentioned this haloform thing. So first, if we were to look at the reaction that we had here, we've got a carbonyl under acidic conditions with bromine. So one of the big things that you should be remembering now is that Br2, despite all the electrons, is an electrophile, okay, meaning it wants electrons. This becomes problematic because we don't really have a good electrophilic site in this material, okay, in our ketone. The other thing that we should note is that we do have H+. So we've got these three different species, and we should be thinking about which should react first. Well, that positive charge is a dead giveaway for that being the most reactive, so we need to neutralize that positive first. Because the bromine was an electrophile, the bromine's not relevant, so I need to find my electrons in my ketone. Personally, I would prefer that you showed an arrow coming from the pi bond, though technically this would be incorrect because the result of that arrow pushing is going to place the hydrogen connected to the oxygen and a positive charge on that carbon. This is a bad Lewis structure, which therefore means I am a bad person because I used the pi bond, the highest energy electrons, to run the reaction. Instead, we should have shown the lone pair. If we use the lone pair, all that's going to happen is that we would be showing the Lewis structure like so, where now every atom has its complete octet, and that oxygen is positively charged. So this is a good Lewis structure, and therefore better than the bad one. But the bad one's nice because what that helps to tip us off on is that we have that unstable positive. Doesn't want to be positive, so it can pull electrons from a hydrogen nearby. This can be drawn on our good Lewis structure. The electrons shuttle so that we move up to that oxygen. The resulting structure would then be our enol. And really what we've just walked through is the keto-enol tautomerization. This running under acidic conditions because of that positive charge that we started with, that acid. The enol is nice because the enol is nucleophilic, which is a great tip-off because we said that bromine was electrophilic. The electrons on our oxygen can come back down. The electrons from the pi bond can react. And this is going to take us to our now substituted enol. That oxygen does not want to be positive. We can ditch that hydrogen solvent. Electrons can come in, remove the hydrogen, and we would end with our final structure with the bromine substituted and our ketone. And we've now done our whole process. Okay? Should have been a useful review. Hopefully that helped out. What happens though is when we switch to basic conditions, things become a little bit more challenging. Okay? And the reason for that has to do with a comparison between our starting material and our product. If we run under basic conditions, the most reactive thing is now a strong hydroxide, which means the mechanism changes, and instead of us reacting with that pi bond, the base comes in and removes that alpha hydrogen. So what we're having these species act as would be acids when we run under basic conditions. Why does that become important? Well, once we've done a single substitution, that structure becomes more acidic. Why is it more acidic? We have an inductive withdrawing effect from the bromine, which then means the next equivalent of base reacts with that product, so to speak, and we continue to do the substitution. So the problem that we got under basic conditions was multiple substitutions of hydrogen for bromine. Okay? The acidic conditions, we didn't have to worry about that because we didn't have that secondary issue. I mentioned it in that first kind of presentation that when we go through and look at our basic conditions system, particularly with this particular functional group, and sorry, oh my goodness, that is not as easy as I had hoped it would be, so we're just not going to worry about it. Under basic conditions, that then repeats out if we have the methyl structure and that methyl ketone, we have those 3 hydrogens that can be substituted. And so what will happen under that step 1 reaction is that we will go through and fully convert that to the tribromine. Multiple substitutions. Okay. That particular piece is now interesting. Why is it interesting? That carbon now has tons of electron density being pulled from it, which means it's going to try and pull electrons. That process weakens that structure, which then means hydroxide now, instead of acting as a base, can act as a nucleophile and can go through and attack. The result, again, officially I'm drawing this slightly incorrectly. Let's actually fix that because we're in that unit. We're going to break the pi bond first. Negative charge. We're now forming what is known as the tetrahedral intermediate. The electrons can come back down. We kick out a good leaving group being our CBr3. The result of that is I now have a carboxylic acid and I have a negative carbon. Well, a negative carbon isn't particularly stable, so what it does is immediately removes the hydrogen from the carboxylic acid, and that then takes us to kind of the important stage. HCBr3 is a bromoform, technically a haloform, and its solubility in water is very limited. Note, to have hydroxide and acid, we are in a water environment, which then means we could see that substance, our bromoform, potentially change the solution clarity. Okay, so we could start seeing it become cloudy. That reaction is all driven because that carboxylate salt is incredibly stable. If we think all the way back to our acid derivatives, then I know we haven't looked at reactivities on them though, but we do have that summary at the very beginning that shows that being the most stable. It's the most stable due to resonance, our favorite word. Okay? How do we finalize our reaction? That's the point of step 2, H+. That step 2, H+, puts on the carboxylic acid or finally protonates it, and we've got our structure. The whole point of this particular reaction isn't to go through and synthesize carboxylic acids. The point of this reaction is to actually identify methyl ketones, which is kind of a weird statement. What we're trying to identify is a CH3 next to a carbonyl. That would be known as a methyl ketone. So the point of this test is to actually come up with some structural information. This reaction happens very, very, very swiftly. So if I mix the reagents and wait, say, a couple minutes, if I see this kind of clouded or cloudy turbidity of the solution, I now know that I've got a methyl ketone. So it gives me structural information. This is known as a classification test. We talked about them with the Lucas test. The ACS still loves classification tests. I don't blame them. It does give us some decent kind of information about the structure and relatively cheaply. But with the price of spectroscopy coming down and its very heavy-handed usage, spectroscopy is going to kind of win the day, and we'll probably see a lot more spectroscopy showing up than we will of classification tests. So I would fully expect these types of questions to slowly be petering out of the national exam. That said, that's probably 5 to 10 years from now. So you are still responsible for this. What they're actually asking here is a repackaging of this. Which compound would give the yellow solid HCl3? So pretty much that whole first statement is just misleading when mixed with iodine and sodium hydroxide. So you could answer this by memorization, or what you could do would be to write out that you're looking at I2 and OH minus. OH minus is a strong base. I2 is an electrophile. I know that in the course of this reaction, I have to get that as a product. So there has to be a way for this iodine to connect to that carbon. So how did that carbon become nucleophilic? That might be enough context for you to trigger and be like, ah, that's right, ENolate chemistry, that carbon is next to a ketone. If that doesn't trigger it, that's okay, because we're looking at a multiple choice exam, and the multiple choice exam would have a variety of answer choices, and you would be trying to identify a carbon that could pick up three iodines. So methyl ketone. You would probably also see a carboxylic acid thrown in there in case you happen to memorize. And then you would probably also see a variety of other pieces, maybe another ketone that isn't a methyl ketone, and you might even see an aldehyde as an example. So again, what you'd be looking for is where could I get a carbon that three iodines could connect to? The only place that that is feasible, finish that out. The only place that that is really feasible is if you have that methyl next to the ketone. Okay? So with that, I'm pretty much going to say I'm done. I did want to point out, because our textbook has a very lovely mechanism drawn out of this, I kind of drew it ugly, but your textbook's got it, and here it is. So with that, thanks for listening, and have a good rest of your day.